but he didn't want to go.
Totally no problem.
Yeah. If he will back, I will ask him to be quiet. It's funny, this condition with the corona, that we are doing everything using the Zoom.
Yeah, I mean, it's good or bad, but in this age, it's suddenly, because of the pandemic, everything become, I mean, the virtual meeting becomes so, how to say, convenient, available. Before that, is reluctant to do that, but now everybody is very good at it.
Yeah, yeah.
Hey, Mohammed. Hello, Mohammed. Hello.
Hi, Doctor.
Yes, Mohammed is my student who from Alexandria, Egypt.
Oh, okay. Nice to meet you.
Nice to meet you.
Neighbors.
Yeah.
Okay. So it's time. Maybe we can start. Revita, are you ready?
Yeah, I'm ready.
Okay. Hello, good morning, good afternoon, and good evening. This is Paul Liu from NC State University. Welcome you to the World River and Delta System Source to Sink webinar series. And today we invite Professor Revital Bookman from University of Haifa from Israel, come here talk about the development of the Nile Littoral Cell during the past 8.2 thousand years. So before I introduce Dr. Bookman, and I would like to mention again, so in the past, 1.5 years during the pandemic, we have already had 100 talks, the source to sink talks, and all of them have already been archived on our YouTube channel and also Bilibili station. So feel free to use them for your research and education. And at the same time, we also maintained a source to sink Twitter account with all kind of update news and announcement for meeting and conference. So all new publications. So please feel free to following us. And the next week, the same time, and we have Andy Vickett from University of Minnesota and his PhD student Shanti come here talk about the views of ice sheet mediated aggradation and incision transform in the upper Mississippi Valley network. So we'll talk about the source next week of the Mississippi River Basin. And as I mentioned, Revita now is a senior lecturer, is assistant professor in the Department of Marine Geoscience, is also Chinese School of the Marine Science, University of Haifa in Israel. As you can see here, she got her PhD from Hebrew University, and then also a postdoc in the Syracuse in University of New York, and then a lecturer and a senior lecturer assistant professor, University of Haifa there. And her main research is the recent and post-marine lacustrine environment, and also the modern anthropogenic process, focused on the later quaternary climate signature in the sediment record. And he's also investigating mass transport sediment was turbidized and submarine landslide sediment transport in the deep Levantine basin. So I would also want to mention in 2016, almost 5 years ago, Revital invited me to visit University of Haifa for 10 days, 2 weeks. And the city of Haifa is very beautiful. As you can see, this is the Mediterranean Sea, and this is the garden on the slope, on the mountain. Very, very beautiful. And even on the campus is sitting on top of the mountain. You can almost see the view, you know, the city and the sea. Interestingly, the plume of the Nile River is reached that point, the Bay of Haifa, and that's the long distance longshore transport, as we talk about in the past year, and all the way from Amazon, the Yangtze, the Mekong, and many large rivers have this longshore transport feature. So today, Revital will talk about that for us in detail. So Revital, now I shift the floor to you. Now you can share your PowerPoint.
Okay. Okay, I guess you can see my screen.
Yes, very good.
Yes. Okay, so first of all, I'm very happy to be here. Thank you, Paul, for creating this wonderful series of talks, of seminars. I often tell my students to go and look on the YouTube channel that you created, because these lectures are really, really wonderful. So today I'm going to talk about the development of the Nile Littoral Cell during the Holocene. And I guess you all know the Nile River, one of the largest system, or the longest systems, river systems on Earth, whose funder of delta is seen here in the satellite. And I'm going to talk about how the Nile Littoral Cell developed, and what were the controls that are responsible for the record that we uncovered on the continental shelf of the southeastern Mediterranean. So the Nile Littoral Cell, as we know it, is a relatively, in terms of geological timescales, is a relatively new geomorphic feature that developed about 250,000 years ago. And we know that from cores that were taken, long cores that were taken from the continental shelf, and reached a rich carbonatic unit only 250,000 years ago. This means that before that, all the Nile-driven sediments were transported into the deep basin of the Eastern Mediterranean, and only later after that, the Nile Delta developed, and we started to see the transport of siliciclastic sediments, of course, sediments along the continental shelf with the longshore currents. And this is this unit seen here in pink. In this work, in this talk, I'm going to concentrate only in the upper part of this record, on the Holocene period, and show how this area developed after the end of the LGM, the last glacier maximum, and sea level rise that flooded the continental shelf. If we look at the sediments today, the nature of the sediments today on the continental shelf offshore Israel, you can see here that this region, the Nile Littoral Cell, is relatively poor in carbonates, and it's mostly made of siliciclastic sands and fines. And it can be seen really nicely in a survey that was done Bookman about 10 years ago, where the continental shelf was sampled in east-west transect, very dense sampling, showing how the percentage of calcium carbonate increases as we go to the north. As we go further away from the Nile Delta, the amount of coarse siliciclastic sediments is decreasing. And in the Haifa Bay, as Paul said, this is let's say the end point of the Nile-driven sediments, and further to the north, we mostly see biogenic sediments in the continental shelf. Also, a very interesting phenomena is the summer Nile flood suspension. Today, we don't see it anymore because since the 60s, or more accurately, since 1964, when the Aswan Dam construction ended, the Nile is dammed, and we don't see any more suspension arriving to the Fan Delta and then towards the north along the continental shelf. You can see here in the picture, a very old picture from the 60s, of the summer Nile flood suspension, bringing a lot of fines, clays, and a lot of dissolved nutrients that were very important for the oligotrophic nature of the Eastern Mediterranean. It can also be seen really nicely in a map of salinity of the surface water along the coast of Israel that was measured during the 50s. And you can see the relatively less saline plume of water in the summer arriving almost to the coast of Haifa, where my university is located. So this relatively fresh water that was arriving from the Fan Delta was transported along the coast, along the continental shelf with the longshore currents, bringing a lot of sediments and nutrients into the region. That stops since the 60s, and we will have I will show you some of these phenomena at the top of my course. What are the primary sediment sources for the sediments that we are working on? So on the left, you can see a map, a geological map with the main geological units in the Nile watershed. You can see here the Arabian, Nubian, and Saharan shields here in pink and in gray. These granatoids are supplying a lot of sediments into the Nile River Valley. And we also have the relatively younger Neogene basalts of the Ethiopian highlands that are discharged with the Atbara and the Blue Nile rivers into the mainstream of the Nile. Another important source, which is also connected to this same geology, are dust storms. Dust storms are also supplying a lot of sediments. So while much of the sediment is being transported by the river itself, we also have dust storms that are transporting dust towards the desert surrounding the Nile Valley, and also to the north in the Negev desert in Israel, and even further to the north, as you can see in the lower satellite image from the NASA website showing a dust storm over the Eastern Mediterranean. So these materials are coming from the same geology, but in most of the cases, they have a more distinct grain size, and they are being deposited on the surface of the sea or discharged by local rivers. Like you can see here, this is a geological map of Israel. This is Haifa Bay, the coast, and you can see all of these small scale rivers that are transporting the local geology detritus, but also dust that was deposited on the surface of the surface. So let's go to the study itself. You can see here, this is just a basic geographical map showing the main features. You can see here the Nile River, the Nile Delta. Another important thing is you can see here the shelf edge, and as we go north, the shelf edge narrows. I plotted on this map also the Sinai and Negev sand dunes and the lowest soils. Also, both of them desert environments that are supplying Aeolian materials. And also a lot of the cores that were studied in the last few recent decades along the southeastern Mediterranean. And you can see that most of them were located along the slope or in much deeper environments. And our cores that are marked here in red and in blue are cores that were taken from the inner shelf of the Nile Littoral Cell. These are cores that are about 7-8 meters. They were collected from a water depth of around 35 meters. We used the radiocarbon to date them. This is the age depth model, a very simple age depth model with a lot of surprises. The cores cover approximately 8.2 kiloyears, 8.2 thousand years. And the sedimentation rates vary between, they're relatively constant, but they're around a few tenths of centimeters per thousand years. So let's look at the different proxies that we measured. We concentrated our efforts on basic sedimentology and also measured geochemistry, trace and major elements, and also strontium and neodymium isotopes that can give us a lot of information about the provenance. So the basic and the first basic analysis that I always think should be done is measuring the grain size. And you can see here for measuring the grain size in the two cores that we already see really interesting features. First of all, in the lecture, the northern core will always be in blue and the southern core, which is closer to the Nile Delta, will be in red. You can see here the percentage of the different grain size fraction, clay, silt, and sand, and the water depth of the core top during the deposition at the specific age of the core. You can see here it covers about 8,000 years. I also measured here, or I also added here the sea level change. It is reflected here as the water depth, but it was reconstructed or calculated from the local sea level that was published by Dorit Sivan. And you can see here, first of all, that the two cores are not similar in terms of grain size. And only the southern core is showing a very distinct change somewhere after 6,000 years. While in the northern core, we see kind of fluctuations all along the core, although we see that we have relatively high percentage of sand and silt at the early Holocene and at the really youngest part of the core. In the southern core, we see a very distinct change that can be correlated to the change in sea level. Okay, we can see that when sea level stabilizes, we start to see a decrease, a very sharp decrease in the grain size and an increase in the clays and the silts compared to the sand. So one interpretation was that it is connected to the change in the depth of the deposition environment. However, we also saw that in the northern core, we don't see that feature, which made us go and look for another possible control on the sedimentation, on the grain size distribution. We think that the reason why we are seeing the very coarse sands at the beginning of the Holocene is related to the sea level rise and the supply of nilotic transgressive sands. When sea level stabilized, we see an end of that phenomena, and we're starting to see the increase in fines. And to explain that better, let's look at the map, the geological history maps that Stanley and Warren, that worked a lot on the Nile Delta, draw during the 90s. And you can see that somewhere around the time interval where we see the sands on the coast of Israel, there is also nearshore sands at the Nile Fan Delta. At that time, sea level is rising, and it is probably eating the front of the Nile Delta, taking all of those coarse sands and moving them downstream, or moving them with the longshore currents to the north, to the site of the southern core that we worked on in this research. Another feature that support this interpretation is the fact that in the cores, we also see a lot of recycled benthic foraminifera, probably representing this transport and recycling along the continental shelf with the longshore currents, bringing these recycled sediments to the southern side. So this was the interpretation of the grain size. Let's look at the TOC calcium carbonate and delta C13 proxies, which are indicators for primary productivity and trophic conditions in the sea. So you can see that here, both the northern in blue and southern in red cores show a very distinct change at just after 6,000 years. So again, both in the sedimentology and in the primary productivity and trophic condition proxies, we see a change somewhere around 6,000 years ago. How do we interpret that? So we see that there is a transition period, while in the calcium carbonate, we see a gradual change. In the TOC and in the delta C13, the change is more drastic. So how do we interpret that? First of all, in the calcium carbonate record, it is possible to see that there is a relatively high percentage of calcium carbonate, although at that time we also see a lot of quartz grains in the sediments at that time. This high percentage of calcium carbonate is also similar to the very young part of the record that was deposited after the Aswan Dam was constructed. So our interpretation is that during that period, or we know from the Aswan Dam period, that the fines that contained the clays are not arriving. So we mostly have calcium carbonate from biogenic sources, local sources, and quartz grains. When we get at the end of the early Holocene, there is a change in the Nile littoral zone. We start to see an increase in the fine suspension, the relatively finer sediments, and then we also see the decrease in calcium carbonate. So the fraction of fine suspension is higher than the biogenic fraction. We also see that we have low productivity at the early Holocene, and it is based on foraminifera species that were collected and analyzed, which I'm not showing here, that are related to oligotrophic rocky habitats. The rocky habitats along the coast of Israel are seen today in the north, where we are far away from the Nile influence. So again, it is the modern condition is kind of an analog to the early Holocene, where we didn't have the fine suspension of the Nile arriving. I will talk later and explain why we didn't see this fine suspension. It's not only because the water depth was low, it was also because we have transgressive sands arriving, but also the fine suspension was stayed in the watershed. And I need also to say that this low productivity on the continental shelf is in contrast to the high productivity that we are seeing in the deep Mediterranean and the deposition of subpropel 1. Also, the delta C C13 on the organic material shows the marine fingerprint of the organic matter. And we are seeing that at the beginning of the Holocene, we are seeing oligotrophic condition, and there is a big change, and we are starting to see the phytoplankton blooms. The phytoplankton blooms are something that characterized the shelf offshore Israel before the Nile was dammed by the Aswan Dam, okay? The lower values of the northern core represent the fact that it is further away from the source of the nutrients. So the phytoplankton blooms were less stronger in the north compared to the south. When we look at the major and trace element, we can see the different sedimentological fractions that I was talking about. So I could not show all the geochemical information that we had. So I used principal component analysis in order to show the main groups. You can see here that we have a nice group of elements that represent clays. We have a group that represents the biogenic fraction, calcium, strontium, and barium. And we also have the silica of the quartz sands. This is the bulk sediment. When we look at the fine sediments, the silica moves to here because we also have silica in the clays, in fine fraction of the clays, but we stay with these two different sources or nature of sediments, biogenic carbonates and clays. And using that, we decided which geochemical ratios we are going to present in order to show the trends that we see. So first of all, you can see here both the northern and the southern core. Again, red is the south and blue is the north. You can see that also in the geochemical fractions, the geochemical analysis, we see a big change somewhere after 6,000 years, although it is more gradual, and it's probably not connected directly to the change in sea level as the quartz grains did, the sand fraction. So we are seeing here a big change that happened about 6,000 years ago. You can see here these two proxies, calcium to alumina and barium to alumina, represent the biogenic versus siliciclastic carbonates. We have a lot of carbonate and in the early Holocene, and it is also seen here in the elemental ratios. We can also see in the fine fraction that we have potassium to alumina and chromium to alumina and titanium to alumina ratios that are higher in the early Holocene compared to the later part of the Holocene. And you can see that the potassium alumina is a proxy for the elite clay mineralogy, which is dust-bearing wind sediment coming from the Sahara. And it is relatively high in the early Holocene. And again, it starts to increase a little bit at the end of the Holocene in the northern core. Chromium to aluminum and titanium to aluminum are proxies for heavy minerals and grain size proxy, and they go together, at least in the southern core, with the relatively high portion of coarse sands at that time period. Another important proxy is iron to silica. Iron to silica is a proxy for the contribution of weathering of the Ethiopian highland basalts that contain the iron in its minerals. So we can see that using this proxy, we can see changes in the contribution of detritus coming or erosion products coming from the basalts from the Ethiopian highlands. So how do we interpret all of this record? So first of all, before that, I want to give a short introduction about the seasonal patterns over Africa, the climate change that, or the paleoclimate change that we had in the past. So first of all, today, the drainage of the Nile River is controlled a lot by the monsoon rains that migrate in a south-north direction. In January, they are migrating towards the south, and in the summer, they are moving towards the north, supplying these summer floods that we used to see in the southeastern Mediterranean continental shelf. But this phenomena is not only something that happens today, it happened also in the past. What you are seeing here is I went back to the geological map of the Nile River watershed, and you can see that during the peak insolation at the beginning of the African humid period, towards the end of the African humid, the peak insolation period, this the northern extension of the monsoon range was reaching the northern part of the Nile River system. However, as we went towards the end of the African humid period, there was a migration of the northernmost extent of the monsoon rain band towards a southern location. Okay, so at the beginning of the peak conditions, peak insolation conditions of the African humid period, the monsoon rains arrived to this northern location. And by today, 8,000 years later, the monsoon rain band migrated to the south, meaning we have less rain in the African, on the Nile River watershed. And this is very important because we are looking here at the Atbara River, the Blue Nile, and the White Nile. These three tributaries are the main tributaries that supply the water discharge in the Nile. And when we look at it, you can see that it's even more interesting than that. We can see that the Blue Nile and the Atbara River are the ones that are supplying most of the water discharge compared to the White Nile. So when this migration is happening, it is affecting the distribution of rain over the Atbara River and the Blue Nile. And the interpretation for our record is that the geochemical composition in the early Holocene is representing the enhanced flow of the Nile River. We are at the monsoon rains at peak insolation. However, while there is a lot of flow in the Nile River, as was seen in previous works, there is a reduced erosion also due to the increase in vegetation cover over the Ethiopian basalts. So we have relatively high content of biogenic material due to the starvation of fines. The fines that are coming from the erosion of Ethiopian basalts are not arriving because the vegetation is covering the surface. At the same time, we also have the transgressive coarse sand transport along the shelf. Okay. However, when we have the end of the African humid period, the picture changes. Also, we can see here the ratio of iron to alumina. You can see here that we here have the cores from the samples from the south and from the north. And all of those samples represent the early Holocene, the lower part of the cores, and they are similar to the local streams that are have less iron in their sediments. When we move to the geochemical composition of the late Holocene, we see a decrease in precipitation over the Nile watershed because the monsoon rain belt is migrating to the south. There is an increase in surface erosion and sediment contribution to the Nile Valley. And there is an increase in fines that are transported with the Nile seasonal floods, with the Blue Nile and the Atbara River with a basaltic signature. And this is why we see the increase in the ratio of iron to silica in the sediment cores, in both of the sediment cores. There is a decrease in relative biogenic signature due to the increase in the nilotic fines, and this is what we are seeing here. There is a decrease in calcium carbonate. And also what we are seeing here, that there is an increase in dust inputs in the past 3,000 years that is mostly seen in the northern core. The reason it is mostly seen in the northern core because the nilotic signature of fines is diluting this signature in the southern core, which is closer to the Nile delta and the input of siliciclast. This increase in dust inputs was shown or was described in other records from cave speleotomes and from the Dead Sea, and it is a real phenomena that is seen all over the Levant. And we will see that we also see it in the strontium sediments. So again, we are going back to the iron to alumina plot, and you can see here that in the late Holocene, our samples are getting closer to the Nile sediments compared to the early Holocene, where our samples were closer to the local streams of the Israeli coast. And last but not least, let's look at the strontium and neodymium isotope ratios. Strontium and neodymium are a very powerful geochemical or isotopic tool that can give us information about the source of the sediments. So we are looking here at the profiles from the both cores. You can see that they are very similar. They are showing a similar trend. And we are seeing a relatively low neodymium, epsilon neodymium ratios at the beginning of the Holocene, and then an increase after 6,000 years. And with the strontium ratios, we see a high volume, a high ratio, and then a decrease in the ratio. And in the upper Holocene, we see again this increase in the northern part. So when we look at the different end members that we have the Arabian Nubian shield, the Saharan shields. These are the volumes of those end members, and we also have the basalts of the Ethiopian highlights, and each one of them have a specific signature. And if I will move to before that, before I move to the field, to the plot showing the fields of strontium and neodymium and epsilon neodymium, I want to show that while here we are talking about these different major end members, we also have a more closer end member, the less soils that are contributing also a lot of sediments into the continental shelf and to the Nile Littoral Cell. These lost soils are being drained by rivers, by the local rivers into the coast. So in periods where the Nile is dominating, we will see the Nile signature, and in periods where the Nile sediment is being trapped in the watershed because of high vegetation, or because of damming of the river, we will see the contribution of the local loess soils. And this is an image from a picture from the Negev deserts showing this cover. It's a very thick cover, a few meters, that is available for transport. So this is the neodymium and strontium radioisotope fields, and this is a little bit complicated plot showing a lot of information. But first of all, let's look at the end members. We have the Sahara granatoids. So this is the field that represents the Sahara granatoids. This is the Arabian-Nubian shields granitoids. And the Ethiopian highland basalts are far in the left up sides, and it is not seen here in this graph. But we have the field of the Nile sediments. These are the characteristics, the ratios of the Nile sediments today. That is somewhere in between or closer to the Ethiopian highlands basalts, which are the most influencing end member on the Nile sediments. We also added here the local sources of the loess soils, in different parts of Israel, the Negev desert, the Sinai region, that are marked here in these pale colors. And on top of that, in this orange-yellow fields, I plotted our samples. And you can see here that they can be divided into three main groups. Okay, we have one group here that is located close to the trital calcite that were attributed to loess soils that were deposited during arid cold periods, and to the Sahara granatoids. And they are probably connected to dust that arrived into the region. Meaning the Negev, the surrounding local deserts. Okay, at that time the northern hemisphere is cooling, and we have the cooling 8.2 event, and it is really possible that this is the main source for those fine sediments. The neodymium and strontium radioisotopes are measured on the fine fraction. The coarse sands are out of our equation, and we are only trying to understand where the clays are coming from. When we move towards the later part of the Holocene, 6,000 to 7,000 years ago, this is the last part of the African humid period, we are seeing that our field is located somewhere between the dust sequences in the surrounding deserts. At that time, we believe the dust that was accumulated previously during the LGM or other older arid periods was remobilized by the fluvial processes due to the increase in precipitation during the African humid period. So it's not the peak African humid period or the main regions where the African humid period affected, but it is known that at the same time in the Levant, there is an increase in precipitation. A lot of flash floods were recorded, and we believe that all of this dust that accumulated during arid cold periods are now moving towards the Nile Littoral Cell. And as you remember, we are seeing at that time also mainly the local streams. We are seeing the transport of sediments by the local streams. When we move to the later part of the Holocene, after 5,000 years ago, we have this field that is moving towards the Nile sediments. We're starting to see the increase in the basaltic Ethiopian highland signature. If you remember higher iron to alumina ratios, we also saw that in the geochemistry. So we are starting to see the aridification of the area, the migration of the monsoonal rains towards the south, increase in erosion, and a lot of sediments that are transported today to the Nile Valley. Okay, so this is my last slide showing this interpretation, this final interpretation, and I will sum up saying that the treated sediments were mobilized to the continental shelf mainly by the Nile River, but also from small local rivers. And all of those sediments are responsible for the sediment blanket that we have today in the Nile Littoral Cell. During 8 to 5.5 kiloyears, the Nile Littoral Cell was characterized by oligotrophic conditions. At that time, we have the sapropel, but the continental shelf is under oligotrophic conditions. And the deposition of transgressive deltaic coarse sands by the transport of longshore currents from the Nile Delta that is being flooded by the last part of the sea level rise. Dust that accumulated in the surrounding desert during previous arid periods was remobilized by wetter conditions at the time period that is associated with the African humid period. And in the last 5.5 kiloyears, a distinct mudbelt was deposited with increased contribution of fine suspension composed of Blue Nile basaltic sources. And in the last 3,000 years, we have a higher contribution of dust that was seen both in the strontium isotopes and in the elite group clays. So I will end with that, and you are welcome to read all of that in a paper that was recently published. And I also want to acknowledge my contributors, my co-authors that are written here. So thank you very much.
Oh, Revital, thank you very much for this wonderful talk, because, you know, now is the longest river in the world, and historically, culturally also very important for us. But relatively to other large river systems like Amazon, Yangtze, and Mekong, the longshore sediment transport is relatively not well studied. And particularly you show the location of the sediment core, as you can see, mainly in the offshore, deeper part, only couple on the shelf of the Israel coast. So we still have a big gap from the near shore to the shelf edge, you know, all the way from the Nile River mouth to, you know, along the shore to the west coast of Israel. So it's a wonderful talk. Great. And anybody, if you have any question, you can go ahead, unmute yourself and raise your hand or whatever, just go ahead to ask. Okay, maybe, you know, when the people prepare the question, I can ask a question. So first of all, you show the river inference sharply increased, you know, after 5.5 thousand years. So about the sea level history in Mediterranean Sea. First of all, during the RGM, how lower of the Mediterranean Sea? It is the same of the rest of the world ocean, almost 120 centimeters, or different?
It is similar. It is similar. And I think what we showed that we thought at the beginning that mostly the sea level change is controlling the sediments or the nature of the sediments that we see. And I think what I feel we did the best was we were able to separate between the different controls. We were able to say what is the role of the sea level rise and how it is affecting the sediments, which is mostly the coarse fraction of the sediment, and how the changes in the discharge of the Nile, the paleoclimatic changes, are influencing the fine fraction of the sediments. And both of them, of course, are arriving to the Nile Littoral Cell, but each one of them is representing a different control over the accumulation.
Okay. Other thing is during the post-glacial sea level rise, what's the common conclusion or common accepted? When did the seawater from Atlantic flow into Mediterranean Sea? Around 12,000 or later, or a little bit earlier?
I didn't understand your question.
So when did the seawater from Atlantic during the post-glacial sea level rise began to flow into the Mediterranean Sea, flooding the Mediterranean Sea?
No, it was flooding the Atlantic. There wasn't a connection with the Atlantic Ocean all over the period, during even glacier periods. The Gibraltar Strait is about 700 to 600 meters deep. So
okay.
It was not closed. You are talking about the Mycenaean period.
I see.
It was flowing all of that time.
It's connected, okay.
It was connected, yeah. Although of course the circulation changed a little bit because sea level was lower.
Yeah. Okay, salinity could be different. Okay, I see that. Okay, that's okay. Let's see if any audience, any question from the audience. Okay. Yeah.
Here.
Go ahead, Mohammed.
Yeah, I'm taking from what Professor Paul said, just said, and you said. There's a change in circulation, a little bit change in the circulation. Did that affect the results? Like, if the circulation is changing, would the rate of the deposition change with it, or it's
well, I think the main change is not the pattern of circulation. The pattern of circulation was probably similar. However, because of the change in sea level, during the LGM, sea level was below the continental shelf. So there were no real longshore currents. So this is one of the reasons why we are not seeing finds coming. But as sea level rise, we can transport with the longshore currents also the finds along the continental shelf. So it's mostly what is exposed, what part of the continental shelf is exposed, and not the pattern itself. The pattern probably stayed the same, but it's the area that is flooded by the sea level. That's the main important part.
You know, we definitely need a couple more sediment core from the Egypt shelf. Then we can compare the proximal record with the distal record in Israel coast. That will make the story more interesting.
Maybe a couple of like seismic lines along the shelf. That would be very beneficial.
You know, that's the Mohammed. We definitely, I need to talk to you. Okay.
Yeah, I would love to work on that. I think this is the part that I always miss in my records, because I want to see what's going on in the Nile Delta, in the continental shelf. And there was a lot of work done on the slope, on the deep turbidite system, but not on the continental shelf.
That's exactly something missing. Okay. Jane Peng, go ahead.
Hello.
Hi, yeah.
Do you hear me? Thank you very much for your very wonderful presentation and lecture. I have a very short question.
Revital, can you change the slide to your conclusion? Otherwise a black screen.
Yeah, I would like.
Sorry, I stopped sharing. One moment. Share. One moment. Are you?
Yeah.
So this is my.
Yeah, that's okay. Yeah, Jian Peng, go ahead.
My short question is, how about the algae and the microfossil, something like that, safety in the sediment cores? Because when we talk about the oligotrophic condition, in the mid Holocene like that. Probably that related to the sedimentary environment change. I'm interested in this section because exactly just have a higher sea level and transpiration. Probably there's more rainfall, bring more nutrients transform from river to the littoral zone. Yeah. And so my question is, how about the algae fossils, like diatoms or some?
Well, that's another thing that we need to study. We didn't study that a lot. There was a work done on the benthic foraminifera, but no work on algae. So, you know, these cores are still waiting to be analyzed for more proxies, that's for sure. And this big change from the early Holocene towards the later Holocene is a very drastic change. And I think in a way it can characterize the change that is happening today with the damming of the S1, the S1 dam, damming of the Nile River. And no, we didn't, it was not studied yet. So, you know, I will be happy to continue this work also dealing with other biological indicators.
Yes, that's great. Yes, I'm waiting your more results from this course. Yeah, thank you very much.
Yeah, that's very cool. So Revita, you also have done some lead-210 accumulation rate.
Yeah, we are working a lot now on the short course, on the upper part of the record, especially because we are also doing some environmental studies, heavy metal pollution in Haifa Bay and also towards the deep sea. So we now measured 9 cores for lead-210, and we are starting to work on them. We just got the results. So it will be interesting to see it. We definitely see the change that is related to the damming of the Nile. We see it very drastically.
You know, this is in the distal end. If we close to a little bit to the south, you know, even the Gaza Strait or close to the border, I mean, the signal may be more significant.
Yeah, exactly.
Oh, very good. We need to do that. We need to do that together. Okay.
Yeah, I will be happy to do it.
Okay. It's great. And so if no any other question, I think thank you very much. And this talk is archived on the YouTube. There will be more audience coming back. You know, they will watch it offline. And Revita, thank you so much for contributing this great talk. And I'm looking forward to our future collaboration with your colleague Uri and other friend over there.
Okay, thank you very much.